I have chosen to speak about Erik's work on the higher infinite in type theory and why I think it's still very relevant today. One of the reasons is that recently I have been discussing universes in type theory together with Marc Bezem, Thierry Cocon, and Martin Escardo. We were all in the Center for Advanced Study in Oslo 1.5 years ago. And we were, asking ourselves basically what is a good type theory for univalent foundation. So I will get to that a little bit towards the end of my talk. But I think that it's quite appropriate to remind ourselves about what Erik did in this work. I have known Erik since I met him for the first time in 1988, when he was still a PhD student. After that, it's been very many visits by him to Gothenburg and by me first to Uppsala and then to Stockholm. And I've always thought of those visits as some kind of highlight of the year. It was always incredibly pleasant and rewarding to talk to Erik and also to other people who passed through Uppsala and Stockholm. People have said many things about Erik, and it's very nice to bring him back to life. One thing that I could add is just concerning, our relationship to type theory and so on. I think he was one of the people that I felt had the most similar view of the foundational aspects of Martin Löf type theory. So let's see now. How do I do this? No, there. Oh. Yes. So now you're seeing two screens, right?
Yep.
Yeah, so let's see if I can stop that. Maybe this one. Yeah, so let me start by just quoting something from a paper that Erik wrote together with Michael Ratjen and Ed Griffer. When Erik was a PhD student, he worked on the domain interpretation of Martin Löf type theory itself, some very important work. And they write, Martin Löf only considered an infinite tower of universes, all of which are closed under the same ensemble of set-forming operations. The next natural step was to implement the universe operator into type theory, which takes a family of sets and constructs a universe about it. Such a universe operator was formalized by Palmgren while working on a domain interpretation of the logical framework with an infinite sequence of universes. So what we see here is actually a very early work of Erik. It was published only in 1998 in the volume from the meeting on 25 years of constructive type theory, which was organized in Venice. And but you can see in this paper that the theory, what's the content of this paper were already basically in place in 1989, so 9 years earlier. It's a very good, introductory paper about, what could we say, that higher universes in type theory still standing today. So for example, he discusses the exact rules for two external towers of universes, a la Tarski, with and without cumulativity. And then he shows how to internalize this by defining a universe operator, a next universe operator. And then he defines a super universe, which is a universe operator closed under the universe operator. And he continues with a more powerful theory of higher order universe operators, where you can, for example, define super universe operators, building the next super universe above a super universe. There is also an interesting discussion about Anton Zetzer's Malo universe, where he discusses whether it's actually predicative or impredicative, finding an inconsistency by using a strong elimination rule, perhaps not the intended one, but a strong one. So this is all very relevant for today, I would say. And I actually thought that I'll show you a little bit of Agda, as we heard. Erik made big formalizations in Agda, so this is part of the credit to him to show a little bit of Agda, showing his work in Agda, I would like to say. So I'll show you some files where I have tried to formalize Martin Löw type theory with one universe as closely as I could to how Per Martin Löw would have written it himself, using his notations as well. And then another file where I show how to define Erik's universe operator, and another file with the super universe. And then relevant for the discussion that we have been having with Marc Thierry and Martin about how you can, inside Erik's extension of type theory, define universe polymorphic things. And there is also an interesting type checking problem if you try to do the cumulative version, what Erik calls full reflection, or in the full reflection version of a universe tower. So let me stop sharing and instead share an Agda file. So can you see it? Yeah, it's okay. You can see my file?
Yes.
Yeah, good. So here is an Agda file. Here is the file head where I make some comments and it's a module, etc. And there are lots of type formers written in Per's notations. Just for those of you who are unused to Agda, let me just show you the rules for natural numbers. So you define the natural numbers is a data type. It's the Agda keyword for inductive definition. So actually in type theory, all sets in this terminology are defined by inductive or inductive recursive definition. And you do it by declaring the constructors, zero and successor, and the types of those constructors. And then you can define the recursion operator. For any family of sets C, if you have an element in C of 0 and you have a step from C of n to C of n plus 1, then you can make a function from an arbitrary C to C of C. And it's defined by the usual recursion equations. So many of you have used Agda, so this is very familiar to you. Some of you have not, but I hope the notation is readable enough. So this is how you define the first universe a la Tarski inside Agda then. So it's a mutual inductive recursive definition of a set U, which has a number of constructors for the empty set, for the one element set, for the disjoint Juno 2 sets, and so on, for all the usual type formers. And it's inductive recursive because in those types of those constructors, we refer for the simultaneously defined decoding function T. And then you declare how the decoding is done. For example, the code for the empty set is decoded as the empty set. So this is somehow the base theory. On top of this, you can define a universe operator. So, well, in Agda, you have to somehow, we are going to build it on top of the previous file, the core Martin Löw type theory. We import some Agda primitives to deal with the Agda notion of level, which I will show you a little bit later how it works. And now we can define the universe operator, and you can see that it's very, very close to the definition of the ordinary universe Alatasky. It's just that we take as two parameters, a set and a family of sets. And we will think of those as, the previous universe. A is the set of codes of the previous universe, and B is the decoding function for the previous universe. And now we build a universe above such a universe. And it's got exactly the same constructors. This is closed under all the usual type formers. But in addition to that, there is a code for the previous universe, and there is something which returns codes for the results of the decoding function. So if we go down to this is of course also inductive recursive, so there is a simultaneously defined decoding function where we have exactly the same equations as for the ordinary universe Alatasky, but we now also need to decode you take little u here, which is the code for what we think about the previous universes, and we decode the results of the decoding function. So you think of B, big B here as the decoding function for the A elements. Given this, we can now build all the universes in the hierarchy of universes. We start out with this zeroth universe, U0, T0, which will, in my notation here, be the empty universe. So we define U0 to be the empty type, the empty set, and T0 to be the empty function. And this is the Agda notation saying that if you do case analysis on an empty set, there are no cases, which Agda writes like this. And then we can build the first universe by using the universe operator on the first universe. The second universe by applying the universe operator on the first universe, etc. And now we can also internalize the infinite tower of universes. We can write a function that I write u prime, which takes a natural number and returns a universe, the nth universe, for a natural number n. So the zeroth universe will be the empty universe, and the successor universe is obtained by applying the universe operator. And it has to be applied both on the universe and on the previous universe and on the decoding function. And then we define the decoding function for the nth or Lth, L for level, universe level. And here is an Agda curiosity that when you do pattern matching, Agda will notice that there is no case for level 0 because that was the empty universe. So it actually erases the 0 case when we do pattern matching on the level L. It will disappear when you do the pattern matching. And with this facility, we can now define some universe polymorphic notion. For example, we can define the code for the natural numbers on an arbitrary level L. And it will be defined like this. There was a code N in an arbitrary thing obtained by the universe operator. And similarly in straightforward way. Yeah, and also here, maybe we should say, of course, this only happens from universe 1 and upwards. There is no natural numbers in the 0th universe in this formalization. And we can make universe polymorphic operations for all the other codings of the basic type formers. This is the decoding of the plus and of the sigma and of the identity types, etc. We can also define the limit of all those finite universe with finite levels. I think we should call it L. by just summing them up. So sigma takes it's a pair of a natural number and the family U prime, which gives the Lth universe for level L. And this has to have a decoding function, basically just saying that when we decode an element of the universe of level L, then we apply the Lth decoding function. So I wanted to show you this just to show how you inside a type theory with a universe operator can kind of represent what you do in Agda with Agda's primitives. The point is really that this sequence of universes, U prime 1, U prime 2, U prime 3, which are sets in Agda's sense, they are different from Agda's built-in tower of universes called set 0, set 1, set 2. So set 0 is an element of set 1. In order to just type check this, I introduce a synonym here with little s instead of big S, but it's only so that I can show this this typing works in Agda. So you have this built-in hierarchy of universes where you have a set 0, set 1, set 2, set 3, etc. And then Agda also has a type level of levels, which is different from the natural numbers in Agda, because it has a limited number of operations, but it also has some extra power. It is a type, so you can write a function which converts a natural number to a universe level. So the level 0 is called L0. So you can map the natural number 0 to the level L0. And you can map the successor levels to LSAC, which is the successor operation on the levels. Agda goes one step further, a little bit in the spirit of the super universe of Erik, but one hasn't wanted to introduce a super universe. One has a kind of type set omega, which can only be used in restricted ways. But for example, you can type something like the large type, which takes a level into a set of level L into the sets of level L, and that has type set of omega. I mean, we could easily make an analog of this using our internal tower U prime L. It will now be a set instead. But similarly to this type up here, we can do this somehow large type as the type of functions mapping a level L to U prime of L. So Erik, of course, takes another step here, which is to make the super universe, which is a universe in the sense that it's closed under all the ordinary type forming operations, but also closed under the next universe operator. So there are these operations, little u and little t, which are there to decode the universe operator called big U and big T. And if we go, it's again, an inductive recursive definition. So it's got a decoding map called S by Erik, decodes elements in big V. And the decoding equations are exactly the expected ones. And the last two ones are the ones where you show how to decode the internal operations inside the set V, the U and the T operations as the universe operators, big U and big T. And now if you want to see what you can do inside the super universe, you can do the analogous constructions that I showed in the previous file. We can make an internal universe tower indexed by a natural number, by doing the internal u and the internal t's. And we can also build its limit, a u omega, which is a kind of representative of the Agda set omega, but now inside the superuniverse V. And we can do this large type analog, which used the type set omega inside V by just taking the dependent function type from the codes n to the coding function u prime. Yeah, so this is somehow what I mean, that when you study the Agda system of universes, Erik's work kind of hovers in the background as some kind of, maybe one would say, a rather disciplined type theoretic way of doing it. But there are maybe reasons for why Agda doesn't simply use that as implemented in these files. So one possible reason is the following one. I mean, I said that Erik used, yeah, so we should say that the universe towers, which I've shown so far, are which don't have full cumulativity. The decoding function is not defined by recursion on the operations of the previous universe, but constructs new sets of codes. But there is an alternative which Erik shows in his paper, which I will just show you by showing how it works for universe, the first and the second universe. So let's just, for the purpose of illustration, make a first universe which just is closed. It's an empty universe, but it's just closed under pi, called the codes for it little pi 1. And so the first universe is here called U1, and the decoding function is called big T1, and it has the expected decoding function. Let's now build the second universe, which is the same as the first universe, but it has a code for the first universe in it. And it has an additional decoding function, which decodes that code, the code of the first universe in the second universe as the first universe. And now what Erik does, but which doesn't type check in Agda, is to try to define now by universe elimination, that is by recursion on the construction of the codes in U1. What happens then is, if you take a code pi 1 of little a, little b, you would expect it to map to pi 2 of the decoding of a and the decoding of the b's. But now when you try to, you would expect to say that, well, it's the family b of x for any x that should be decoded by the T1, 2. But if we do that, can show a little bit of Agda type checking here. You will see that this won't work, right? Because you expect an argument of B here to have type T1, I mean the T1 of A, the decoding for the first universe. But what you have is the decoding for the second universe of what is obtained by taking the decoding of the A in the second universe. And those two things are not definitionally equal. They're not convertible. They somehow couldn't be because, well, we haven't really defined T1, 2 yet. So how could Agda know this? And indeed, if we try to do, sorry, if we try to refine this goal here, Agda protests and says that it doesn't work, it doesn't type check. On the other hand, there is nothing wrong with adding this equation. It's just that it doesn't type check. It's a semantically correct equation. The right-hand side can be kind of justified by some realizability model, or it can be justified by the Martin Löw style meaning explanation. So there is nothing wrong in adding it, but there is something strange going on with the type system. So maybe it should be a primitive. So let me go back to my slides. Can you see them? Yeah, good. So yes. Yes, what I wanted to say was, so I wanted to somehow just rather quickly remark that why is this still important today? Well, Erik's work was really the starting point of several extensions of even more powerful universes. Quantifier universe by Ratjen, Griffer, Palmgren, a Mahler universe by Anton Setzer. All of this was input to my own work with Anton on induction recursion. And then Anton Setzer has continued trying to make even stronger universes. I mean, Anton and I had a schema for induction recursion, which kind of explains how induction recursion is actually, from a syntactic point of view, quite a mild extension of the W type. The schema that I had previously for inductive types is a very mild extension of the W type. One can kind of see that the schema doesn't add any strength to the W type. Whereas if you allow induction recursion, you get the possibility of doing many stronger things, and we don't know what the end of this process is. I think it's important to emphasize that there is a difference between induction recursion as a number of universe constructions which of a specific W-like form, and the general notion of induction recursion, where you just say you can kind of inductively generate a set and simultaneously a recursive function together with it, not necessarily fitting into this kind of straitjacket that Anton and I stipulated. And this is what Anton uses in his work. Why do I find this so very interesting, and why is Erik's work so very important? Well, I mean, it extends the scope of the notion of type theoretic constructivity into the higher infinite. It provided crucial motivating cases for induction recursion. And I think importantly, it provides challenging cases for foundations. Why are these higher universes constructively valid? I think when Per Martin Löw thought about his meaning explanations, this work was not yet there. And there is a question to ask, in what sense do these meaning explanations provide an answer to the question of why they are constructively valid? So for me, they provide important food for thought concerning the meaning of Martin Löw's meaning explanations. Some of you have heard me talk on this topic, and it's a sort of a topic in its own right, which I can't go into here, but I think something more needs to be said with respect to Per Martin Löw's original papers on meaning explanations in order to somehow clarify the status of these higher universes, why they are constructive. Saying something like they are predicative is not sufficient, I think. It's to me, predicative sounds like a subjectivistic notion, and you want to have something more objective. So to, yeah, so sorry, I hope I'm not, yeah, no, I think I still have some time. So the other direction where I think Erik's work is relevant is the study of the Agda type system. So Agda's type system came at the time, or I should say the proof assistants in Gothenburg, they started, well, the intentional proof assistants in Gothenburg started in about 1991 when Thierry came to Gothenburg. And it was at the time when there was Martin Löw's logical framework, and there was an idea to build a proof assistant based on Martin Löw's logical framework. So what I showed you is using a part of Agda which only uses Martin Löw's logical framework. It has one type set of sets or small types, and it has dependent function types. And then the idea is that the data types are all defined inside set. For example, natural numbers are defined inside sets, but there is also a pi set constructor, which should be separated from the pi type constructor. And there is an internal universe UT, which should be separated from the universe set, which is also of the character of a universe, a la Russell. So Per's idea was that his previous formulations of type theory, of the types in his previous formulations of type theory, should all be kind of constructions in set. And this function arrow more has a sort of meta level function of being a way to represent rules. Yeah,
Peter, your highlighting is extremely exciting for us, but he's not giving us what you expect when we're looking at it.
Oh, I see. Okay, maybe I should stop it.
The highlighting is hiding the content of what's highlighted, I'm afraid.
Yes.
Oh, okay.
But in a visually very interesting way.
Yes. Can you see the cursor?
Yes.
Yeah, good. So maybe I should just use the cursor. Anyway, so what is Agda's logical framework like? Well, so rather than one type set, it has a whole sequence of sets, an infinite tower, and it has this special kind set omega that I showed you in the Agda files. Then it has this special type level of universe levels, which enables universe polymorphic definitions by quantifying over it. And then there are level operations like, which I showed you, the zero level, the successor level, and also the least upper bound of two levels. And there is a level algebra making it's a sub-semilattice with some extra equations for the next level operation and the zero. And then, you know, you have these dependent function types with appropriate level constraints. The big question is, of course, why extend Martin Löw's logical framework? And I think the reason why this was done, you know, so maybe other people in the audience know this, or the answer to this better, but I think it was simply from a practical reason that you wanted to work with these universe a la Russell sequence rather than encode it using the internal universes as I showed you in the previous files. And you know, users immediately started using the meta level function space rather than the pi sets as perhaps was Per's initial intention. Yeah. So the starting point for our discussions in Oslo was that Martin Skardu came there, and he showed us his very nice implementation of univalent mathematics in Agda. And basically what Martin said was that he was really, really fond of Agda's approach to universe polymorphism. A lot of his definitions are universe polymorphic. He has special nice notation for it. But the problem is that the Agda type system is a little bit ad hoc, as you can see with this set omega with the somewhat unclear status. And what we wanted to do was to somehow try to kind of provide some foundation for it. So this is the last slide where I just summarize a little bit what our discussions have been about. Universes in Agda is a very old and persistent topics. We have had now 33 Agda implementers meetings, and in at least half of them, there has been a topic of discussions about, how should the universes be implemented. There are many things to discuss: Tarski versus Russell, open versus closed. Should you have cumulativity? Should you limit the theoretic strength? What should be the algebra of universe levels? So in this work in progress, we are suggesting several different theories. And one basic idea is to have a notion of level judgment. We declare something to be a level, and we make it possible to assume that something is a level variable. One version of the system is inspired by Voevodsky's universe polymorphic system, where where you can actually make judgments dependent on a number of level constraints. And there is a constraint solving algorithm inherited from previous work by Mark Besem and his co-workers. Another line of thought is to try to abstract, in the sort of spirit of Voevodsky's, initiality conjecture, whereby type theory is looked at as CW categories with families with extra structure. We can also analyze this theory by kind of having some appropriate notion of universe tower structure in the language of generalized algebraic theories, and hope to show that Tarski versus Russell are just kind of different initial objects of suitable such categories. So that's the end of my talk. I would like to finish by thanking the organizers for organizing this very nice meeting, where we have remembered Erik and seen the great range of his work. And also, since I had to miss the toast for Erik, I have here a minimal amount of whiskey, and I will make a final toast to Erik, and I will leave the work to Henrik and the organizers. Thank you.
Right, unmuted now. So Peter, there's one axis that's not on your slides that interests me, which is kind of natural from a category theorist point of view, which is when type theorists do universes, their decoding functions are up to equality, whereas a category theorist would most naturally think of the decoding of a code being just isomorphic to the thing that you want. So is there anything that we can say about the relationship of that weaker notion to this more strict notion?
Yes, I think so. An observation due to Martin is that the non-cumulative version in Erik's implementation actually can be seen as cumulative up to isomorphism.
Right.
Because you can, they will be somehow decoded in the codes.
Yeah, they won't be equal, but they'll be isomorphic.
Codes, but they are isomorphic if you turn this universe into a category.
Yeah. I guess if you have univalence, then the isomorphisms would become equals, but
indeed.
Yeah, following up on that, have you looked at what univalence would mean for these higher universes?
The starting point was to write a polymorphic univalence axiom. It should be possible to write a polymorphic univalence axiom in the system we want. It's more been on the level of providing the theory in which we formulate univalence, rather than thinking about, yeah, no, I mean, I think that's somehow the connection with univalence. We want to have an appropriate basic type theory with appropriate notion of universe polymorphism, in which we can formulate the univalence axiom and a lot of other things.
Thanks. Next, Thorsten, then Johan. First, Thorsten.
Yeah. First of all, Peter, thank you very much. I mean, I've read Erik's paper a long time ago, but I think it's a good idea to revisit it. And by the way, it would be nice if you share your ACTA code. Yeah, it's one thought. You define these sort of universes, super universes, inside set, so inside set 0, right?
Mm-hmm.
So now you have both. You have got the super universe, and actually you have the super universe in every level. Yeah. So have you got? Is there any reason why we should believe that ACTA's type theory is consistent? I mean, it seems to have a hierarchy of super universes. That sounds really dangerous.
Yes, but so I think this is the sort of thing which, yeah, you know, when in my work with Anton, this is the kind of thing that we, mainly Anton, were worried about, right? Because you when you determine the proof theoretic strength, you get something, you can show that you have a Mahler unit. It's proof theoretic strength is some of this admissible Marlows, and then omega admissible in admissibles above it, I think, So I think it is consistent in that sense, and there is a reason for it.
Okay. I mean, I have to admit I'm very suspicious also of the sort of free use of induction recursion. I mean, there is a way of a limited induction recursion which can be justified by inverse image interpretation, but which doesn't create universes which just fall from the sky. So I'm personally more conservative in this respect. So,
mm-hmm.
But anyway.
Yeah.
Next is Johan, and after that, Peter. Johan?
Yeah, thank you. So on the last slide, I think it was, you had something about algebraic conditions for universe levels or something similar.
Yeah.
So can you say something more about that?
Well, so there was one thing which was, sorry, I can share this. I think an observation, maybe Thierry who made it first, is that we don't need a zero. It seems that what Martin implements is basically independent of having a zero. So we just need a subsemi-lattice of having the least upper bound operation, the sub operation, and with the equations for plus. But the zero doesn't seem to play any role. This could maybe have some kind of a conceptual reason for this.
Next is Peter, and then after that, there's Anton. Peter?
Thank you. Sorry, by the way, Anton, I'm not jumping the queue. It seems a Zoom host doesn't get a raise hand button, so I messaged Erik instead. But yes, thank you for a very nice universe time. And in the last bit where you were talking about the universe polymorphism and how one might kind of add this kind of polymorphism to ACTA, how does it compare? Are you able to say something about how it compares with the universe polymorphism that Koch has been using for the last few years? Is it sort of aiming for something a bit different or something fairly similar?
So I don't know too much in detail, but I think, isn't it the case that the Koch universe polymorphism is a bit more restricted than AGDA's? They don't have something analogous to set omega, I believe. So they are already doing something similar to having level judgments, but perhaps there is someone who is more familiar with this than me. I mean, a comment in this work is, of course, that the development of universe polymorphism was started by Gerard Huet and then also by Randy Pollack and Bob Harper. And this was a bit independent of the work on super universe and so on. And this was more thought of as some kind of practical thing, I think. So I'm not sure to what extent it had an impact on the more theoretical work on the higher infinite. But yeah, I don't know. So a conjecture that someone may refute or affirm is Koch's universe polymorphisms roughly the same as having level judgments?
Right. That yes. In those terms, I'm not sure I can give a good answer to that.
Also, I also don't know too much Koch, but you don't have level variables in Koch, I believe. Do you?
Yes, you do, but they're quite carefully hidden. Mm-hmm. They're rendered more inaccessible to the user, but they're there under the hood, and they're powering the universe polymorphism. Right, Koch for the last few years, it has quite a powerful universe polymorphism, but it tries to make it invisible to the user so that the user isn't too tempted to try and sort of jump in and externalize it and make it meta and get frustrated that then they can't. So, right, I think, thank you.
Okay, next is Anton and then Steve. Anton?
Yeah, two things. The first thing is I want to comment on what Thorsten said regarding doubts about is ACTA consistent. I think what is really problematic about ACTA is it's not the fact that it allows induction recursion, though that is pretty consistent, but that it allows combinations of induction recursion and induction. And with Frederick, we tried to make sense of, to get control over induction, and only got really the very basic things of it under control, and having this extreme generality is really not something which we understand very well. So a model of all of I would say still core of ACTA, not this kind of experimental features which have been added, is very would be quite challenging. But from Peter's talk, I started to realize during a talk. So we introduced in ACTA these level universes, and the reason we introduced them is just to reduce the syntactic overhead we get, because everything which can be done with these level universes could be done by just creating universes. There's a certain limit because it definitely gives you a tiny little bit more proof-theoretic strength, but that's not really significant, I would say. But the real thing is you introduce these levels of universes because you want to get this kind of accumulative universe. And I think a theory of induction based on Russell type universes would be very interesting to do, and then introduce corresponding features into ACTA. So of course now I'm contradicting myself. First I was criticizing ACTA for not having a model. Now I want to extend it already. But I think that would be it would be quite interesting feature to add some form of general Russell universes. So one could, for instance, look at the super universe from Erik, whether one can make it Russell style as a starting point. So that might be quite interesting. It would make life easier. It would not add something which you couldn't do before, but it would make life easier.
So there is actually a early unpublished version of Erik's work. I think it may be the one together with Ed Griffer, where there is a super universal Russell.
Oh, that's great. Yeah, you can.
I'm sorry, can I
send
just...
me the link? Can you send me the thing?
Sure, sure.
So I want to just, I mean, Anton, I'm a bit surprised that you think that induction causes problems, because it's actually conservative. I mean, you can reduce it, unlike induction recursion. So why do you think this?
The thing is just we don't have a no. It's not that no, it's not that I believe it's inconsistent, but we don't have any model.
So induction, we can reduce to W types. So what's the problem?
Yes, but to get the whole, so what you would need is to get the full type theory of ACTA has so many different features. For instance, for me, the interesting thing is that although never ever anybody was investigating the notion of induction, it was already there. So the difficulty is really, can you somehow get a complete model of ACTA which covers all these nested universe, induction, recursion, etc., and getting getting a formalization of just of induction was already so complex. Sorry, that was.
I think that was the signal for Steve Pickers.
I kind of hesitate to ask this question because it seems fantastically theoretical, but yesterday, when I was giving my talk, I was suggesting as part of it that if you, I was suggesting that the cause of the problem of universes and needing a hierarchy of them actually arises from using function types, admitting function types, because it amounts to a discontinuity. And the suggestion there was that if you work with a purely positive logic, and one where topology is, you have to take account of topology all the time, then the question that we see of universes and hierarchy of universes would at the very least come in a very different form, and not arise in the way that we see it. So leaving aside the practicality of whether you can actually do this, develop good mathematics in its purely positive way, do you agree that it seems plausible that universes arise from using arrow types and non-geometric types?
I don't think it's not the line of thought I have at all pursued, but
the basic idea yesterday was, rather than universes, you use something like the object classifier, a space of sets.
The universes are object classifiers, at least in univalent.
Yes, exactly.
I don't think that's true, because if you take, as I was saying, U arrow U would not give you the answer that you get for object classifiers.
Completely agree. I mean, universal object classifiers. So that's it.
There's a theorem in the hot book showing that they are,
so
in a suitable sense.
So what would U arrow U be in hot?
functions from one universe to another. What's the problem?
Well, the object classifier results would give you that they're covariant functors from finite sets to sets. In other words, diagrams over finite sets. Would you get that in?
I think you're using object classifier in two different ways.
Isovariant, at least. They respect isomorphisms. They have to respect isomorphisms, but not necessarily non-isomorphism maps. Right.
So in the geometric version, they would have to be functorial and preserve filter colimits. So I think you can't. It's oversimplified to say that the ones in hot are going to be object classifiers, because they won't behave with respect to arrow in the same way.
I think there's a misunderstanding of terminology going on here.
In hot, the U arrow U in hot is small families on the universe. In topos theory, it's all objects, no size constraint. If you take the endomorphisms, geometric endomorphisms of the object classifier, it's just the object classifier, it's equivalent.
I think people are using object classifier in two different ways.
Right, they're two different things.
At least.
I think there's a misunderstanding of terminology between type theorists and the topos theorists going on here.
I have a feeling it's rather the functions which are different.
And I think also between one topos theory and higher category theory, there's again a ambiguity of terminology.
So, but can somebody explain to me what the ambiguity is? I mean, to me, I know object classifiers classify all monos, and an object classifier classifies all small maps, and that's exactly the meaning in type theory. So where's a misunderstanding?
In topos theory, in traditional topos theory, I think it means something else.
Yeah, in topos theory, there's a geometric object classifier which classifies the geometric theory of an object. It's a topos, and a Grothendieck topos, and mapping into it from another Grothendieck topos is equivalent to that topos. So that's a different notion of object classifier. It's just it's a coincidence of words, I think.
So the points of the object classifier are sets, basically. In any Grothendieck topos, there can be points in that.
It's a different notion of object classifier than the one that is meant in hot and in higher category theory.
So you agree it's different?
This is all very entertaining, but I don't think we're asking Peter questions.
True enough. Any more questions to Peter? Otherwise, I think we should wrap it up. So let's thank Peter again. And that concludes this final session. Thanks to all the speakers.